So that is mainly about poles. So now let's look at zeros. Now, of course, the first thing about zeros, at let us say the zero frequency, that is S equal to the zero frequency. What can you say about the, oops, okay. Yeah, so at the zero frequency zk, what can you say about the transfer function h of s? It becomes 0. So which means I can say that my output in the Laplace domain is how much? 0. Again, this is for a non-zero input, right? That's important. I find that for a non-zero input, the output is 0 at a complex frequency s, that is the zero frequency, right? And the other point is the zero location is a strong function. I will say it strongly depends on the location of input and the output. Again, we'll see it with an example. And in general, you can have zeros in the circuit because of the following reason. So let us say your output V out of s, let us say it is some non-zero function, non-zero value V of s. You want this to make it equal to 0. What is the simplest linear operation I can do here to make it equal to 0? Huh? Sorry? What should I do? Okay, I mean much more simpler. I mean, like, yeah, let's say multiplication is difficult. I don't know multiplication. I'm a first standard student. Huh? Yeah, I mean, you add minus V of s. I give you 5 chocolates. You should have 0 chocolates. You give it back to me. That's all. So this is one way in which you can have 0 in your circuit. That is, the output voltage might be obtained as sum of two different voltages, and at some complex frequency they can add up to 0. And if you want to have something to be 0, you should have two things adding up. That's all. Or you can have a case where, let us say, you have two currents with different frequency dependence adding up to the output, flowing through some output impedance to give rise to 0. Basically, at the output you should have two voltages getting adding up, or two different currents getting added up, and those two currents must have different dependence on the complex frequencies. Right? So let's look at some example. So let me take simple case. Say something like this, 1C1 C2 something. So here let's see if we have 0 or not. So here, do you think I have the output obtained as sum of two different voltages here? Is the output obtained as sum of two different voltages? Yes? No? No? I mean, the output voltage is voltage across this capacitor. It is just one voltage. We have not two, it is not like I have two voltages getting added here. Do I have two different, I mean, two currents getting added to the output? Yeah, what are the currents? Where are the currents flowing? One through the capacitor, sorry, resistor, one through the capacitor. So from the input to the output, I have two different currents getting added, and those two currents will have different dependence on the complex frequency S, because one is a capacitor current, one is a resistor current. So at some complex frequency, this can add up to 0. So we'll have 1 0 here. So maybe I'll take another example. So say you have something like this. Say R1, R2, C. This is V in, this is V out. So here tell me if the output voltage is obtained as sum of two different voltages here. I have the voltage as voltage across the resistor plus the voltage across the capacitor. Again, since it's a capacitor voltage, that will have a different dependence on S. So here you can have a 0. We'll see. I mean, but does it make sense that the output is obtained as two different voltages? We'll see the 0 indeed. So now let's say instead of defining this as my output voltage, let us say define this as my output voltage, say it's V out hat. Now do you think at the output I have two different voltages getting added? Only one voltage? Do I have two different currents getting added to the output? No, I just have one current here. So do I have 0 here now? So that's what I'm saying. That's why I told the location of the 0 is a strong function of what you define as the output and where the input is applied. Okay. This is unlike pole location where pole doesn't depend on the input or output. So this is essentially a physical. This is how in circuits you can have zeros, but there is a foolproof way to detect if you have 0 in a circuit or not. I'll just briefly explain that. So let us say I take a third order case. So I have three capacitors C1, C2, C3. So let me write an example transfer function. So denominator, let's say I have a constant term, plus I have an S term. The S term will come due to what kind of elements? Capacitors or inductors. We have only capacitors, so I'll have S term coming due to C1. Let's say C1 times some R1, C2 times some R2, C3 times some R3. Similarly, S square term will come from which? Yeah, it will be due to product of two capacitors. So let us say C1, C2 times something, C2, C3 times something, plus C1, C3 times something. Similarly, S cube term will be due to C1, C2, C3. So now this is the denominator. Let's write the numerator. Let us say numerator I have a constant term some k naught times, let us say I have 1 0. So which means in addition to the constant term, what will I have in the numerator? One S term. So once again the S term will come due to the capacitor. So let us say this is some C1 times some RA, C2 times some RB, C3 times some RC. This is how the transfer function polynomial will look like. So here if let us say I make one of the capacitors to infinity, right? So what I am doing is I am making one capacitor to go to infinity, right? So which means in the numerator I have a C1 term that is going to dominate if I tend that to infinity. So I have C1 times something. In the denominator also I have a C1 term. Remember we already discussed I cannot have a C1 square term. I can only have C1 term. So here also I'll have a C1 term that will dominate. So if you tend this C1 to infinity, this will be a 0 or this will be 0 or a non-zero number. This will be non-zero. Yeah, I'll say it's finite non-zero. And the same holds good if I tend any other capacitors also, right? C2, C3, doesn't matter. Let's say it is C2, C3, anything. So let me remark the observation. If I tend any of the capacitors to infinity, I find that my transfer function, or I will say the output in the Laplace domain, it is non-zero. Correct? If I find that if I tend one of the capacitors to infinity and the output is non-zero, does my transfer function have a 0? The transfer function does have a 0, correct? So which means I can say h of s has a 0. So again might be counterintuitive, but we assume that we have a transfer function which has 1 0. In that if I tend any of the capacitors to infinity, I find that the output is non-zero, correct? So let us say now the transfer function does not have a 0, which means how will the numerator change? This term will not be there. Let's say I strike it off, and then I do the same experiment. Say I tend one of the capacitors to infinity. Yeah, because numerator will have just the constant term k0, denominator will have a C1 term that will be dominating, so this will tend to 0. So which means I can write the state here. If h of s has no 0, and then I tend, let us say, any of the capacitors to infinity, the output should go to, yeah. Is the statement clear? Might be slightly counterintuitive, but you just have to wrap your heads around it. So which means, based on this, can you suggest me a foolproof way to detect if I have a 0 or not? We just made an observation that if I tend any of the capacitors to infinity and the transfer function has a 0, my output will become non-zero. So based on this, what might be a test you can suggest to check if I have a 0 or not? That's all. So in your circuit, you take any capacitor, you tend, if you are able to make any capacitor to infinity and you still find that the output is non-zero, then you have a 0. Correct? If you are making any capacitor to infinity, but you find that the output is 0 for all of this, then you don't have a 0. Fine. So I'll just remark it here. Basically, you tend any capacitor Ck to infinity, and let us say the output is non-zero, which implies we have a 0. That is an easy way to check if you have a 0 or not. So remember, this is just for testing if I have 1 0 or not. Let us say now the transfer function has 2 zeros. How will the numerator change now? I'll have an s square term. So let us say I have a, let me write in different color maybe. So let us say it's s square times, again I'll have C1, C2 term times something blah blah blah. Correct? Now tell me what might be an extension of this to check if I have 2 zeros in the circuit. Yeah, so the idea is to check if I have 1 0 or not. I was tending one of the capacitors to infinity, and if for any of those combinations, if the output was non-zero, we could conclude that I have 1 0. Now what I do, I'll take 2 capacitors at a time, tend both of them simultaneously to infinity, and for this case, if I find that the output is non-zero, how many zeros I'll have? Right, so I can basically generalize this. Where will I generalize? I'll write it here. So let us say you tend Ck, Cj, Cl to some, I'll generalize. Let's say you are able to tend k of n capacitors to infinity, and my output in the Laplace domain is not 0. How many zeros I have? K zeros. That's a very simple check you can do. Again, we can take some examples and then see. No. The idea is, let us say you have 4 capacitors in your circuit. Okay, C1, C2, C3, C4. You tend, let us say, one C1 to infinity, C2 to infinity, C3, C4. For any of this, if the output is non-zero, you have 1 0. Similarly, for checking if you have 2 zeros, you choose 2 out of the 4 to infinity. You have 4 C2, so you have whatever, right? How many combinations? So for all those, you try for all combinations. If for any of those combinations, if the output is non-zero, then you have 2 zeros, and so on. So let me take the same examples we saw, so that so now we can easily check. Let us say this is the circuit, right? So here let's check if you have 1 0, right? So I have two capacitors. So let us say I try to short C1. I'll make C1 to infinity. So I'm shorting C1. So what happens to the output? But let us say I take the other capacitor C2 and short it. Is my output 0? No. So which means I have 1 0. So I can also check if I have two zeros. So I try to short both of them simultaneously the output is 0. So I don't have two zeros. So I just have 1 0. Yeah. Basically, to check if I have two zeros, I should be able to short two capacitors simultaneously, right?
Technically, it should be 0, but
Yeah.
I'm not able to decide due to V input. And
No. Yeah. I mean, so that basically you're shorting V into 0, right?
yes.
It is, you can think of it as an invalid connection technically because you're saying V in equal to 0, but you get the point. This is not a connection we are making. In the simple check, you see that this is not happening.
Neither it is 0 nor it is something else.
I mean, basically that's technically an invalid circuit. If you do this, it is saying 1 equal to 2, right, or 2 equal to 0, because I have two things. This is setting the voltage to 0. This is setting to V in. It's technically invalid, but yeah, I mean, it's okay. Right. So similarly, let's take this. Let us say I define this as my output. I short this capacitor to 0. What happens to the output? Non-zero. So which means I have 1 0. Now if I call this as my output, I short this capacitor. What happens to the output VO hat? So do we have 0 in this case? No. If the output goes to 0, you don't have a 0. So that's why it is very important to understand that the location of 0 is a strong function of the output and the input. So which means next time if someone gives a circuit and asks you if the circuit has zeros, what should be the first question you ask? Where is the output and what is the input? Without knowing that, you cannot make a comment about if the circuit has 0 or what is the location of 0. Cool. So that is about finding if the circuit has 0 or not. Now calculation of 0 location is even slightly simpler. So what you do is the following, right? See, I know that at my 0 frequency, that is S equal to the Zk. What can you say about V out of S? At the 0 frequency, V out of S is 0. So to find the 0 frequency, or I mean 0 frequency meaning the Zk frequency, I'll assume that my output in the Laplace domain is 0. Okay. So then you can solve the circuit using KCL. See, typically you solve the circuit using KCL and find V out of S. In a normal scenario, V out of S is the unknown to you. But here the situation is slightly reversed. You know what is V out of S. You want V out of S to be equal to 0. So you assume that V out of S is equal to 0 and try to solve for the circuit. And here, instead of finding V out, you will find the value of S. Technically, you find the unknown voltages. Here, one of the voltages is known to you. Because that voltage is 0. So which means the natural unknown is now the complex frequency S. You solve for the circuit so that what is the value of S, that will make this 0. So here you can quickly check. So let's say this voltage is 0. You apply KCL here. I have two currents flowing. So what is the current flowing through capacitor in the Laplace domain? V in of S times, the current flowing through the capacitor is the voltage difference by the impedance of the capacitor. What is the voltage difference across the capacitor? V in of S, V in minus V out, V out to 0. What is the impedance of the capacitor? 1 by S times in Laplace domain. Okay. So which means the current is thank you, SC2. What about the current flowing through the resistor? V in of S by R1. Sum of these two must be equal to what? Sum of these two must be the current flowing here. V out of S is 0. So no current flows. So I know for a fact that my V in of S is non-zero. which means to satisfy this equation, what is the value of S? Yeah, it should be minus 1 by R1 times C. That's what I meant. Typically you don't solve for S, right? You solve for V out. But here I know what is V out. So one of the unknowns is gone. So the unknown that you are now interested in is S. So similarly, we can solve for the right side circuit also. Let us say this is my V out. So again the same thing, I know V out of S is equal to 0, correct? So if this is 0, what is the current flowing here? V in of S by R1. So that current flows through this impedance. So V out is 0, which is basically V in of S by R1 times R2 plus 1 by SC. I know for a fact V in is non-zero, which means S should be minus 1 by R2 times. So that's about, that's how you find the location of zeros. So again, you solve for the circuit. Typically you solve for unknown node voltages, but in your case you will know one of the voltages is 0. So that is no longer the unknown to you. The unknown will be the complex frequencies. That's how you go about solving. Fine. So that's about basics of poles and zeros.